Good morning, all. Today I am presenting our research paper, the title of which is Studying the Effect of Type of Surface Passivation Layer on Performance Parameters of AlGaN MSM Detector. So, starting from abstract, it is mentioned in many research papers that surface passivation of photodetector is required. This is required just to minimize the surface leakage current. And conventional types of passivation layer for AlGaN type MSM detectors are based on silicon dioxide and aluminum oxide. The utilization of passivation stack. This is studied in few research papers. That's why we have proposed the idea of using surface passivation stack of Al2O3 SiO2 based passivation layer stack for the enhanced performance of photodetector. So for this, we have selected MSM detector. The MSM detector which we have selected in our present work, that is based on AlGaN material, and beneath the AlGaN layer, we have used aluminum nitride just to minimize the surface defects in the AlGaN layer, and the substrate is sapphire. So we have utilized square-shaped MSM detector with and without passivation layer just for comparison the performance parameters of both the detectors. Silvaco Atlas simulation tool has been utilized. We have used a program in DevWorld, and we have extracted various performance parameter, key performance parameter of detector like dark current density, electric field, photocurrent, recombination rate, and even photocurrent to dark current density ratio. And in our program code, in the Atlas code, we have utilized adequate material properties for AlGaN, aluminum nitride, sapphire, and gold metal contacts for the proper functioning of the detector. So this is the passivated MSM detector, where we can see that the topmost layer, which is sky blue in color, these are metal electrodes, gold metal electrodes, which are also known as Schottky contacts for the detector. MSM detector. MSM detector mean metal-semiconductor-metal detector. So anode is the metal. Semiconductor layer is AlGaN, which is pink in color, peach in color here. And cathode is another metal. So metal, semiconductor, metal, this is the interdigitated electrode pattern for the MSM detector. Between these electrodes, we have utilized a passivation layer stack, which consists of aluminum oxide over mean. Below that, silicon dioxide layer has been used. The color of aluminum oxide is red in color, and silicon dioxide is sky blue in color beneath that layer. Below the AlGaN layer, green color layer is representing aluminum nitride layer, and blue color is representing sapphire substrate. And these metal electrodes are internally interconnected. So this is the proposed structure we have utilized in our present work. And other features of structure designs are mentioned in this slide. The electrode dimension. These are these dimensions play very important role for the functioning of the detector. That's why uh, to utilize the electron dimensions in very good manner, just to decrease the dark current, we have utilized double spacing as compared to the width of the metal electrodes. So spacing is the S is the spacing between metal electrodes. This is the spacing between metal electrodes, anode and cathode, and W is the width of metal electrodes. So we have utilized double spacing. just to decrease the dark current. The thickness of single passivation layer. We have also utilized single passivation layer for the analysis purpose. The thickness of passivation layer is taken same as the thickness of metal electrode layer, that is 20 nanometers. And the thickness of passivation stack is 10 nanometer each. Mean aluminum oxide layer is also 10 nanometer and silicon dioxide layer is of also 10 meter, just to become 20 nanometer total in thickness. And thickness of AlGaN aluminum nitride layers is 500 nanometer each. Mean the thickness of both the layers is taken equal. The intensity of illuminated light, we have focused a light on the photodetector so that we can convert the incident light into electrical current, output as a photocurrent. So we have utilized the intensity 1 watt per centimeter square, and the wavelength of light is taken as 270 nanometer. The wavelength basically corresponds to the band gap of the material, the semiconductor material, which is aluminum gallium nitride. Now, what is the proposed methodology we have taken under consideration in the present work? 3 detectors we have selected. The first one is without passivation layer. The second one is based on single passivation layer. And the third is based on stack, the passivation stack, which we have discussed earlier in the previous slide. So we have designed these all structures in Silvaco simulation tool. The performance parameters of detectors have been extracted using Tony plots, cut line plots, IV characteristics plots, and the key performance parameters has been compared. These have been compared for these all detectors which are under investigations. So this is the first result we have shown before you, that is the dark current density plot. So this is the dark current density plot of MSM detector, which is based on this passivation stack layer, and we have considered the average dark current density value. Average dark current density here in this plot is near to 6 into 10 to the power minus 8 ampere per centimeter square. So we have taken average value. And this is another graph, another plot where we can see that this is the IV characteristics. Along y-axis, we have shown photocurrent, cathode current in amperes, and along x-axis, anode voltage up to 20 volt. This is the reverse bias voltage. Up to 20 volt we have considered for the simulation purpose. This IV characteristics plot is showing that the red color line, which is a horizontal line shown in this plot, this is representing dark current. Dark current is very much low in our design because we have taken double spacing as compared to width of the electrode fingers, and the green line representing photocurrent. The photocurrent tends to start around 15 volt, and after that it is increasing up to 20 volt, and the value of this photocurrent in ampere is mentioned in our performance parameter table. So it is coming about to 8.5 milliampere. So this is a table which is showing that there are 4 types of detectors. The first one is without passivation layer. The second one is based on silicon dioxide passivation layer. The third is based on Al2O3 layer. And the fourth one is based on Al2O3 and SiO2 passivation stack based layer. We have compared these 5 performance key performance parameters of photodetector: average dark current, density, which is an ampere per centimeter square, peak electric field near the electrodes under reverse bias. Basically, electric field is very important whenever we want to attract the photo generated carriers towards electrode. So higher electric field mean the low recombination rate. So the next column is representing average recombination rate whenever incident light is focused on the detector. This is in per centimeter cube second. The average photocurrent density is also noted down, and the last column is representing the ratio between photocurrent to dark current density. So this is the multiplying factor of 10 to the power 10, and here we can see that the highest value of photocurrent to dark current density ratio is with passivation stack layers, which is 600, and the lowest dark current, because we are minimizing the surface states of the detector, due to which the dark current can be reduced, dark current density can be reduced, and which is coming out to be 5 into 10 to the minus 8 amperes per centimeter square. So here in this table, we can see that the highest electric field, the highest photocurrent to dark current ratio has been obtained with this particular passivation stack layer, and the lowest dark current density out of these all, which we can see here, this is with passivation stack layer. And the average combination rate is almost, same, which is very low in this case also. So now we can conclude in our present work that the passivated detectors, the passivated detector, whether it is based on single layer or passivation stack layer, these are recommended, because in comparison to the non-passivated detectors, because these passivation layer, these are required just to decrease the surface leakage current of the detector. And after a simulation of all parameters of the considered detectors, we have concluded that the detector which is passivated with stack, that exhibits lowest dark current density but the highest electric field and photocurrent to dark current density ratio, as compared to unpassivated and single passivation layer based detectors. And in addition to these parameters, we have also analyzed that similar IV characteristics and similar UV cutoff wavelength we have observed for these all detectors mean the passivation has no effect, low effect on these parameters like photocurrent, UV cutoff wavelength. And after this simulation work, we can conclude that um, we can recommend that the stack passivated layer based detectors provide reliable operation, high efficient performance for the UV detection applications. So these are the references we have used in our present work. Thank you all. Thank you for your patience.